Excellent. Well, for all of you that have joined us this morning, we are talking about scaling CO2 heat pumps, challenges, opportunities, and next steps. We're very excited to have a panel of just absolutely fantastic experts in this space, and we're looking forward to a really good discussion. I will just remind everyone that there is a Q&A button there you can hit for questions. There also is a chat. If you'd like to introduce yourself or say hello or make a comment there, that's not part of the formal Q&A, more than happy to do so. We have staff that are monitoring both, so we'll do our best to keep everything pushed toward the discussion. So thank you very much. Let's go forward. Adam, would you like to go through the agenda and some context for the webinar?
Yeah, so today we'll just start off with some introductions, welcoming the speakers, give a little context around what's going on with CO2 heat pumps at the moment. But before we do that, just run through in the agenda. We have Rami Moussa speaking from an MEP perspective on the case for CO2 heat pumps. Isaac Simpson will be following on the project delivery and owner perspective. And then David Kaneda will provide the electrical perspective, and then finish off with some industry resources by me. So I do want to start us off by grounding us on some of the on-the-ground work that's been happening right now. So ProspectSV is currently leading two of the first CO2 heat pump demonstrations in America, both of which are funded by the California Energy Commission. And these demonstrations showcase this technology in two very different environments. And together, they can give us a clear picture of how Flow, who is the manufacturer of the CO2 heat pumps for this demonstration, how Flow's CO2 heat pump can scale from large commercial buildings to industrial cold storage operations. So just quickly, in the context of large commercial buildings, we installed Flow's 20-ton heat pump at Lawrence Berkeley National Labs Flex Lab facility in Berkeley. Then on the other end, we have our industrial demonstration at Strauss Family Creamery in Rohnert Park, where we're installing a 60-ton CO2 heat pump to support multiple refrigeration spaces at their dairy manufacturing facility. So when I say that ice cream and eggnog and Greek yogurt are at the forefront of innovative heat pump technology, it's kind of true. But yeah, so just a big appreciation for both LB&L's Flex Lab and Strauss Creamery for giving us the opportunity to pilot this new technology. And shout out to our partners who you can see above, who are our core partners for delivering this project. And if you want to learn more, keep up with the results, ProspectSV's website is the place for it. There will be a QR code towards the end of the webinar that will take you directly to there. But I mean, speaking of CEC funded programs, Doug, do you also want to introduce perhaps one
Yeah,
more that's on the horizon?
yeah. So we have an exciting announcement. We are very proud to announce we just recently received a notice of proposed award from the California Energy Commission for a third CO2 heat pump project. We will be developing a from Flow Environmental Systems' original design for its 60-ton system, from which we created a 20-ton subunit. We're going to be now developing a 7.5-ton, roughly, CO2 heat pump system with a single compressor that will be simultaneously delivering heating, cooling, and domestic hot water. That developed system will go into production for a demonstration unit that will be mounted at the 34th and San Pablo housing project, which is underway today. This happened because an incredible team came together. First of all, the core team from our demonstration projects with Flow previously, but bringing in the East Bay Asian Local Development Corporation, IBALDC, David Baker Architects, Energy Engineering 350, which are the core team for the building project, alongside our engineering partners and national lab partners for the technology demonstration. We're all incredibly excited about this, and we'll be telling you more about it as this comes in 2026.
Awesome. So with that we can move forward with the webinar and have Rami. Rami, you can introduce yourself and perhaps speak on more about CO2 heat pumps from an MEP perspective. Let me stop sharing screen so I can give you the opportunity to do that.
Yeah, it sounds great. Thank you. All right, let's make sure we've got the right slide sharing. Everybody see that screen now?
Yep.
Beautiful. Okay, excellent. Gosh, that blueberry cobbler on the Strauss Creamery slide really caught me off guard. I don't know if everyone's as excited for Thanksgiving dinner as I am. All right, so to jump into the CO2 heat pump application from the MEP sort of designer perspective, and how do we think about how this system fits in to our the way we think about buildings today and how we apply electrification technology. Let's start from the very top here. Um, when we think about just this movement that's happened over the last couple of decades toward decarbonization and electrifying buildings, it all really starts from some of the state approaches and these building performance standards being driven by local municipalities. Right. We have states now and utilities really focused on developing renewable energy infrastructure and energy production so that we have clean energy going into our buildings and our infrastructure within our cities and towns. And with that renewable energy, once we fully convert infrastructure in new buildings and existing buildings from combustion fuel sources to electric, we can decarbonize or eliminate the greenhouse gas emissions associated with operating that infrastructure. So there's this strong drive towards electrifying or making that fuel switch towards electricity in our buildings today. Um, in California, natural gas use makes up about 3/4 of heating and or space heating and water heating, or rather conversely, space heating and water heating make up about 3/4 of all of the natural gas consumption within California. Um, and so this is a huge part of that fuel switch is how do we efficiently and cost effectively make that switch for these types of systems. Now, when we look at the type of equipment that's in use today, it's usually, way over here on the left, these natural gas boilers. And this chart is an illustration of the range of efficiency that we see in these types of equipment. So essentially, how much energy do we put into the system versus how much do we get of the system? And with our conventional heating systems, natural gas boilers, for heating hot water systems or steam heating systems, they range in the basically 50% to just under 100% in the lower to mid 90s for energy in versus useful heat out. Now, as we switch to electrify, the first stop in efficiency, most similar to the conventional approaches, is electric resistance. We're running electricity through a resistor and we get useful heat out of that. That process is about 100% efficient. Sounds pretty good, right? The challenge is with the amount of cost associated with electricity versus gas, that financial picture can be a very difficult one to overcome without really efficient building infrastructure like envelopes and passive energy approaches in buildings. So what we have most frequently utilized for an energy efficient and power efficient approach to electrifying buildings is heat pumps, right? And it's not magic, it's the refrigeration cycle, but with every unit of energy we put into that system, we get 2 to almost 4 units of heat out. So 2 to 4 times as efficient as electric resistance. And with that, we can reduce the amount of power needed in our electrical infrastructure and in our increased distribution to that new equipment. And that creates a more viable solution to electrify our buildings today. Now, this push for electrifying buildings is relatively new from a municipal or a legislative perspective. There have always been the leaders in industry and pushing for zero net energy and effectively eliminating emissions in buildings. But as a society, this is a relatively new trend. And because of that, we're still catching up to a lot of the product development that went into things like condensing boilers and really eking out every bit of efficiency from combustion-based heating systems. So this next step in that efficiency story for heat pumps, as we can see here, is really pushing into using some different refrigerants, using a little bit of different process. And CO₂ does that. It pushes our efficiency from 2 to 4 times as efficient as electric resistance to more like 2 to 5 times or even greater in more ideal conditions. So we can utilize even less power. We can put even less strain on, say, existing power infrastructure and really solve some of the challenges that we see with conventional heat pump systems. So that's one side of the picture, is we can make that next step in efficiency and performance. There's a whole nother layer here to policy within what constrains building design and equipment design, and that is around refrigerants. So when we rely on heat pumps for our heating sources, we are using the refrigeration cycle. We are using refrigerant. And there has been an unprecedented shift in the types of constraints we have on phasing out harmful refrigerants and in lieu of more practical or lower harm substances. So in the last couple of years, we've seen the phase out of R22 and now even more conventional or more frequently used R410A. So equipment that was basically installed last year will not really be able to be maintained, will not be able to be replenished with leaked refrigerant in 2035. R410A is going to be very difficult to come by. So we've got to think about what are those next steps? What are those next technologies and refrigerants that can be used? That doesn't just impact our ability to maintain things, but also the cost to maintain existing equipment. From what we saw with the R22 phase out in 2020, in just the span of 2 years, the cost increased fivefold for that refrigerant to replenish. So the operating cost actually of keeping this equipment around increases dramatically. That's something that we've got to be cognizant of as we design our facilities going forward. Now, as I mentioned, that policy driven by the EPA is really pushing the global warming potential of refrigerants lower and lower. From the top of this chart, we're seeing those phased out in lieu of this middle section of the chart here with R32 and 454B. We see this global warming potential dropping further and further. You can't go much lower than CO₂. Carbon dioxide is basically the reference point for all other GWPs. And when we think about sort of future proofing or getting ahead of legislation, that is about as good as it will get. And seeing the historic trend, we do continue to see more and more stringent requirements on refrigerants. Okay. Now, as we relate this consideration to new construction versus existing buildings, we have some criteria here on the left that are regular focuses in this electrification design scheme. With new construction, we can basically build around these constraints. We know how much space will be required. We know how to optimize for power demand when we have control over the space we need in a project for these systems. And we can design systems for the most optimal operating efficiency points for the equipment itself and throughout the building. With existing buildings, when we are faced with replacing combustion-based systems like boilers with heat pumps, there are some very different constraints we have Heat pumps are bigger. They require more space. They are heavier. They have a different noise profile. Uh, so there are a number of these pieces that we have to navigate and get creative with solutions in different existing building conditions. Another piece I really want to hit on here is that with conventional refrigerants, there is a very specific operating range for supply hot water temperatures that we can hit. Something unique with CO₂ heat pumps is that they can actually meet more of the conventional heating system operating conditions with hot water temperatures up in that 160, 180 degree range. So there's an opportunity here for CO₂ to kind of cover a different range of equipment than conventional can and present some additional value. Let's review some of those that sort of ideal value trade-off or proposition that the system brings here. If we were to replace an existing system or try to integrate CO₂ heat pumps into a system that use conventional equipment like chilled water systems, natural gas boilers, and natural gas domestic hot water heating equipment, we could replace that with fewer pieces of equipment. And with one of the pieces of equipment out today, it can serve all three of those duties with the same piece of equipment. And so in doing that, we have fewer points of connection for power as opposed to electrifying the boiler and then electrifying domestic hot water equipment. We can actually fit all of those services into a single power connection that ideally would also fit within the existing chiller capacity or connected load. So we have the ability to retrofit this equipment in within existing power infrastructure. For conventional heating operating ranges where we may see 180 degree, 160 degree heating hot water, that CO₂ heat pump can do that. It can provide that higher grade heat and avoid costly upgrades to heating coils within the building that would be required for lower temperature, more conventional heat pump technology. Okay, so some great opportunities there. And last but not least, in cold climates, the efficiency of CO₂ as a refrigeration process is far improved. So even at 0 degrees outdoors, 0 degrees Fahrenheit, we're still operating above COP of 2, or twice as efficient as electric resistance. Conventional refrigerants are typically sub 2.0, maybe 1.8 or so. And so you actually see an improvement in the amount of power that would be required versus conventional refrigerant systems. Okay. Right. And last but not least, from my end, we think about these systems as, okay, they are new. It's scary. How do we incorporate this equipment? And the first thing we want as designers is precedence. Where has this been done before? How reliable is the equipment? And the exciting thing here is these uh, applications within controlled facilities like at LBL that Doug and the team here has been working on. We have test data. We have data to see, okay, how does this really work out in the field before it's been implemented at large scale commercially. So exciting things to come here, and we're excited to see this product evolve and the industry evolve around it for how we can decarbonize buildings in this strategic sort of next generation fashion.
That's excellent. Rami, thank you so much. So I want to encourage questions. So as a way to encourage questions amongst the 50 or 60 people that are on this webinar, I'm going to ask you a question real quick, Rami.
Yeah,
Uh, from your experience, I want to say this. I want to say this right. Are there scenarios or opportunities where the CO₂ heat pumps are really the best choice for small buildings? We talk a lot about
right.
large commercial, but what about small buildings, the other 96% of buildings out there?
Right, right. Small buildings are a unique case where they oftentimes actually don't have centralized systems, right? This is a centralized heating and cooling plant within a box.
Mhm.
And typically existing smaller buildings use unitary equipment that kind of distribute uh, packaged equipment over a roof or smaller water heating equipment. And so in that way, they don't necessarily need this level of intervention, really. There are products that already address some of those unitary applications where we have smaller equipment that's required.
Excellent. Thank you so much. So next we have Isaac Simpson, DMG North, talking about this challenge from a customer perspective and an O&M perspective. Isaac, I'd love for you to share your slides. And thanks for everybody that's starting to join in the Q&A. We'll answer where we can and do a group discussion as well. Go ahead, Mr. Isaac. And you're muted, Mr. Isaac. Isaac, you're muted.
I hit the unmute button twice, Doug. I don't know why it wouldn't work. Here,
There we go. Okay, good.
I needed a technical challenge to start off.
Yeah, and we kind of see your speaker view on slides, by the way.
Okay.
Sorry, everybody. We'll just take a minute here.
One more minute. Well, I can introduce myself while I figure out why that's not sharing. I'm Isaac Simpson, sales director at DMG, and here to talk to you about what the customer perspective is on CO2 heat pumps, and really just a lot of the questions that we get when we start talking about. My share is not going to cooperate.
Oh, no.
Is that, are you?
There we go. Beautiful.
Thank you. But I think really just talking about where CO2 heat pumps make sense. I think Rami set us up perfectly for expanding the customer side of this discussion. And you start out with roughly in the United States we have about 6 million existing commercial buildings. Surprisingly, about 1.8 million of those are actually all electric. Those all electric buildings tend to be smaller, and they tend to be in areas of the country where we have very, very low cost electricity, and not very strict regulations on how we use electricity. So there are small there's a significant number of all electric buildings in existence. And then we move on to the over 4 million targets, if you will. So if we have about 4 million commercial buildings that are using primarily natural gas as the fossil fuel, for heating, that's really the CO2 heat pump opportunity. I think Rami did a great job of setting us up. The buildings that we're building brand new from scratch, we can do a lot of things that are really smart about how we design that building envelope, design our water temperatures for heating, how we ventilate that structure. There's a lot of things that we can do with a brand new building. Our existing buildings are where the real challenge is, and that's what is so exciting about a CO2 heat pump that can deliver that high leaving water temperature to reuse that existing infrastructure. A big thing about decarbonization and getting our buildings greener is the more that we can smartly reuse those resources in our building, the piping and things like that, the lower carbon footprint that upgrade is. So if we're having to knock down buildings to the ground or rip out all the components, it's extremely costly and it has a very high carbon footprint. So the more that we can reuse infrastructure, the better we can. And so what are we looking for? We're looking for really feasibility, like where can we put these CO2 heat pumps where it makes sense? And the first thing that we look at whenever we look at an existing building is those boilers that are there, and are they sized right? buildings that are 30, 40 or more years old typically have a heating plant that is significantly oversized compared to what their needs are today. Change in use inside the building, just occupancy, how that building's being used today versus when it was first built out, the design temperatures that it's operating at, the just the factors of safety factors on safety factors when we're sizing boilers. The boilers are probably oversized, and we need to figure that out because if we just look at, and we would not do that, but if we just looked at the nameplate value of that boiler and tried to buy a heat pump to fit that, it would be way oversized and probably way out of budget. We probably would not have the electrical or physical or other space that we need to make that work. So the first challenge in decarb, whether it's a traditional heat pump or a new CO2 heat pump, is right sizing. After that, then we have to figure out the infrastructure. Again, we've touched on this briefly, but there's a cost to this equipment, but then it's what are we connecting to? What piping and coils and pumps and other control points are there in the existing building that would maybe have to be changed if we went with a conventional heat pump versus a CO2 heat pump? So the CO2 heat pump, the first thing is if it's a system that's been designed to deliver 180 degrees to all the terminal units, to all the coils out there in the building. The first question is could we maybe turn that heat down just a little bit and operate more efficiently? Maybe that could be at 170 or 165. And then secondly, if we can figure that out, how much of the existing system can we reuse? I know that on several projects that we've looked at in the past, when we looked at 120 or 130 degree water coming from one of these conventional heat pumps, the equipment cost wasn't the problem. It was the repiping the building and changing all the coils, the massive amount of labor, and actually just having to really tear the inside, the guts of the building out and replace that became the limiting factor. So feasibility was really about, can we change the equipment without having to change everything else? And that's the big first cost comparison, is what all is it going to take to make a CO2 heat pump work at that facility? Just does it pencil out, right? Then we look next at the energy use. We're comparing in every different market what the cost of gas might be versus electrical costs, because we're going to an all-electric system. How is my heating bill going to change? How is my cooling bill going to change? How efficient are these systems? Does that make sense? Does that help pay for this transition? A lot of buildings that are looking at the change, whether it's to a traditional heat pump or a CO2 heat pump, they're taking a phased approach. They're not doing everything day one. I think that's really smart. They might be leaving part of their boiler plant or one of their chillers in place while they convert, say, half of the building over. And then, as budget allows and as technology continues to progress, they're moving to the next phase and the next phase as they gain trust, as they gain experience operating the system, as their facilities people get more familiar with it, and they're more comfortable with the technology. They deploy it further and further. Maybe they start with one building on the campus and expand to the next building or then the next building. So this phased approach, I think, is something that a lot of customers just kind of intuitively has a common sense to it, and really does work. And then you take a look around and you say, is there any money out there to help me decarbonize my building? And the answer in a lot of areas is yes. There are utility programs and rebates through municipalities, state incentives. There's sometimes tax breaks involved, which can really change the math on what is being installed. So that like for like boiler, or even if code allowed an electric boiler, that may not make sense. It may make a lot more sense to go with the much more efficient system and get or take advantage of some of the incentives that are out there. I think the other thing that, and we Rami briefly pointed to this, is Traditional refrigerants are being phased out over time. The cost of maintaining your building using traditional refrigerants will continue to increase. Each time that there's a repair or a leak to a system, the cost of that repair is more expensive with traditional refrigerants. CO₂ is an extremely inexpensive refrigerant. It has one, two, if it does get released, it's a much safer refrigerant to get into the atmosphere. So, and in our experience, the way that leaks have occurred or could occur on a CO₂ system, they're a tiny little pinhole. And what's cool is you can almost find it by finding a little dot of ice right on the pipe where the leak has occurred. So very little refrigerant. We're not having massive losses. When it is, it's a very inexpensive and safe refrigerant to have escape. And so as these regulations continue forward and synthetic refrigerants are continuing to be phased out, CO₂ is a great option for that reason. And there may be other drivers. I mean, certain businesses have adopted decarbonization goals. This can help with that, and so CO₂ heat pumps can help the math from a number of different ways, and we're here to help you with that. I just want to take a minute and talk about why some people are like hesitant about CO₂ heat pumps. What are some of the concerns that we hear from customers when we bring this up? Because immediately they're going to start asking questions about the technology. How long has it been around? Are parts available to service this? Are there people who know how to work on these systems and can install these systems? And these are the same questions I had when I first looked at some of the technology we now have been working with the last 2 years. Are people going to be comfortable with a system that has an operating pressure that is roughly twice what, say, a 410A system would have been operating at? And we look around at our commercial installations where it's been used on the refrigeration side, and thousands of very, very popular name brand stores that we all shop at are using CO₂ in their refrigeration systems for their cold storage or walk-in and reach-in systems. So those pipes are in tens of thousands of facilities around North America that we all visit every day to get our groceries. So these systems are out there, they're widely deployed, and that operating pressure is not something to be concerned about. As far as parts go, the new commercialized systems that we're seeing are based on the industrial systems that are already out there, which means the parts are already on the shelf. We can service these things with what is available today in your local market. And we have been training people to work on these systems for about the past 15 years, and those efforts are just going to continue. And I'll touch on that a bit more in just a second. And then
Before
I
you
think
move on, Isaac, if you wouldn't mind, while you're on the subject of customer concerns, could you maybe just cover what kind of safety systems are specifically associated with the CO₂ heat pump systems that kind of deal with the pressure issue?
Sure. So first off, it's just it's the type of pipe that we install. So we install something, that is going to be appropriate. So Schedule 40 stainless steel is what we're using to connect these systems. They're rigorously tested both at the factory and then at the job site before we start it up. And they're going to, I mean, number one, it's the testing. Number two, it's the sensors. And then the shut off sequence. So there's kind of safety on safety on safety. And then within the commercial system that we're talking about here that is flow, there's multiple points of shut off and isolation that are very easy to access. And the system has redundant points of isolation of the refrigerant and safety. So we're not, in the event of a tiny leak, it kind of takes care of itself, but we also have multiple points of service and safety built in throughout the system. So,
Right.
two and three different ways that we could think of it failing, and we've kind of addressed every one of those.
Okay. Thank you so much.
And then to being first. I think some people are very, very excited to go first, and then there's commercial building owners, and that's not the typical mantra of a commercial building owner. They need to know that it works and that it's going to deliver for their tenants and that it's going to be safe and be reliable and have good uptime. And so we look at Europe, CO₂. Domestic hot water systems, over 21 million units have been deployed over about the last decade and a half in domestic hot water heating. One, CO₂ is a heating technology that has been widely deployed for your domestic hot water. Additionally, in the refrigeration and industrial application of both heating and cooling throughout Europe, we have about 95,000 sites. That's two or three times that in terms of the number of systems. So a significant number of systems have been deployed. And then in the refrigeration side, at least 3,000 sites in the United States have been deployed over the last about 10 to 15 years. So it's just that the data for how many CO₂ heat pumps that are doing either water heating or an air source heat pump like we're talking about that would do comfort heating and cooling. There's not good data that I have been able to find on just how many of those systems are out there. We're deploying these test sites around California just to prove out the technology and address those concerns. But the idea of using CO₂ for heating is not new. I think what is new is using it for heating and cooling in our HVAC systems as well as our domestic hot water. And this new approach is something we're really excited about. So we can honestly say that if you are choosing or thinking about going with CO₂ for heating, you're not going to be first. This is a technology that has existed and is in use. We're using it just in a different way than it has traditionally been used. And to help support that, and this is kind of what I want to end on, is just the regional training that's available through DMG, through numerous other organizations in our industry that'll help people understand how to work with CO₂ as a refrigerant and just be comfortable and safe when they're operating with that type of system. The applications, where to apply this, where does this make sense to use it? How do we safely install it and make sure that it will not leak, that it will operate problem-free for a long time? How to troubleshoot the system if we are having an issue? How do we work on these systems if we do need to service them and figure out what has gone wrong? And then just for the facilities people that are on site interacting with the systems every day, how do they operate them? How do they maintain them? What's unique about these systems compared to, say, another heat pump or a
Right.
boiler or chiller that they're used to servicing? So
Excellent.
I think a big part of getting owners comfortable with this technology is making sure that we've helped the people that are going to interact with these pieces of equipment every day
Yep.
get comfortable with how to operate them.
Great. So thank you so much for that. We're just slightly over time, so I'm going to rush along. David Kaneda, Ideas Consulting, you're going to speak to us about this topic from an electrical perspective. Thank you so much.
Okay, sounds good. Let me fire up my screen. Can y'all see that?
Yes, beautiful.
Okay, cool. Um, so the electrical impacts, let's get to the important stuff. No, just a joke. This is focused on HVAC. So very similar to the heat pump, the mechanical side, there's a big difference between new construction and existing construction. So with new construction, there's not a huge amount of additional cost and a design that has to be done. Um, And kind of when you look at the increase in electrical costs, there's potentially larger savings in getting rid of the gas infrastructure if you're building a new building. Um, and if you look at CO2 versus standard heat pumps, since they're more efficient, then circuit sizes can go down and the amount of energy uses can go down. So that's pretty simple. Where it gets a little bit more complicated is when you're talking existing construction. So the first thing, of course, is we're constrained by the size of the service, the size of the equipment that's already existing, right? And so if that number goes up, then there's potential to exceed the size of the service and or exceed the size of the panels that are serving the AC unit that you potentially want to use to feed the heat pump unit. So what are some of the things that can drive those numbers up? One thing is if you're in a location where the heating load is much higher than the air conditioning load, say, Minnesota or Alaska or something like that, then that increase in load could uh, be significant. If you're using traditional heat pumps that instead of like a CO2 heat pump that could supply really hot temperatures, um, some of these existing heat pumps technologies use supplemental heating, which is electric resistance heating if the demand is high when the temperatures are really low. So that could increase your demand. And then the last thing is if you're using separate heat pump water heaters from uh, heat pump heating and cooling systems, then the water heater could be running at the same time as the heat pump system, and that can increase your demand. Um, so increasing your demand can, at the kind of micro level, can require new circuits and or replacing panels and things like that. But the big thing that people worry about is if you increase the service size, then there's a fair amount of expense involved, and a lot of times there are delays in getting that service upgrade approved through the utility. And that could not only add cost, but cause construction delays. Then the last thing is um, CO2 heat pumps can decrease circuit sizes. Number one, as Rami was talking about. Um, and this technology where you're using one device that can do multiple things like um, heating and cooling and domestic hot water, then the fact that you use one compressor and one circuit can reduce the demand. Um, and that can save you both on energy use and on circuits. Um, and then the last thing that I thought was really fascinating about some of these systems is if you're using one compressor that's doing both heating and cooling, now, think of a refrigerator where you're like cooling the inside of a refrigerator and then you're dumping the heat out into your kitchen. And then you're using an air conditioner and you're taking the heat out of your kitchen and dumping it out of the building, right? Now you've used two different compressors to kind of like move heat. If you could actually take that heat and use it to heat water at the same time that you're cooling, your efficiency can go way, way, way up. So Rami's talking about, we were talking about it was, what was it, Rami? Like a COP of 7 or something like that they're talking about, rather than a CO2 of 4 or 5, which is like unusually good, right? Now you're talking huge COP. So I think that's really exciting.
Yeah.
That's it.
Wonderful. So first, thanks to everybody that's been posting questions in the Q&A, and thank you, Rami, for answering incredibly detailed, really interesting questions by Cooper Ackerman, by the way. Those are some tough questions. I do have a few questions for folks. Again, we'll try to address as many as we can. Some of these are quite detailed, and I'd prefer for Rami to maybe handle those in print. But uh, I'd like to start with a couple of things from the customer perspective, and perhaps Isaac, you might know this. Rami, you may have some insight as well. From the standpoint of financing, are lenders and insurers treating CO2 systems any differently from conventional equipment? Uh, any friction from getting those projects financed? Could you kind of tell some war stories, preserve the identities of the innocent?
I I have not. I mean, for just the CO2 systems that have been used in retail, industrial manufacturing, I'm not aware of any insurance or premiums above what they would normally be using. Again, this is a non-toxic, totally natural, very safe refrigerant. It's just its operating pressure. Also, a lot of the new refrigerants that have the lower, kind of GWP that we were referencing, some of the R32 or 454B, those are partly flammable, and I think that there's more concern, although we have not seen any, I don't think insurance premiums or other finance risk profiles from there. There have been just a lot of industry discussion about having either a flammable or partly flammable refrigerant piped through the building. So there's a
Right.
lot more concern with some of the everyday refrigerants, I would say, than there would be with CO2.
I liked how you described one time, Isaac, what happens if there was a CO2 leak.
Yeah, it tends to be just a tiny little hole that is then literally sealed with a block of ice. I mean it builds it builds up a little ice. That white dot on the pipe is your answer to where to fix it, and there you go.
Right. Excellent. So a couple of questions, and again, we're addressing a number of the very detailed questions that came through type. And again, thank you, Rami. You're pulling the yeoman's work here. Uh, so first, like you mentioned, there's a lot of CO2 refrigeration, especially in like the grocery space and things like that. Very few CO2 heat pump products in the HVAC space, at least in the United States. So, two-part question for y'all. One, why so few products today from your standpoint? And is it a different picture in Europe, for example?
Well, I can Rami, I don't know if you wanted to jump in on that, but I know that I think that their refrigeration application has been widespread and large scale heating has been widespread. I think that the difference here is where we're doing simultaneous comfort heating, cooling, and domestic hot water is really just adapting this system. And there's some new technology that is a part of some of these. Flow is a new commercial system. There are some custom solutions that are out there. I mean, anytime you say the word custom, we're talking about a multiple on the cost for that
Yeah.
technology. So I think it's just an industry shift that's happening.
Mhm.
I think that everybody was really comfortable with the traditional refrigerants, and weren't as concerned about some of these issues. So if you're not concerned, we were worried about ozone depletion 20, 30 years ago, and when we got rid of the refrigerants that were causing those problems,
Mhm.
literally the ozone hole in our atmosphere has literally been able to repair itself over the past decades that we have not been doing that. I think that there just has not been the same focus on refrigerants and their impact in global warming. We've talked about a number of other things that are impacting global warming, and now that we see the focus here, CO2 comes right to the front of the pack for what we can do to help from our industry.
Anything to add to that, Rami?
Not at the moment.
Okay, thank you very much. Speaking of Europe, then, the other natural refrigerant, or one of the other natural refrigerants, because we would say it would be CO2, propane, and ammonia. So there was a question, and I think it's a good one. Propane is at least fairly regular in Europe, as I understand, as a refrigerant. Uh, any insights that the panel might bring on application of propane in the US? It's often uh, not allowed here per fire code and others.
Yeah. Yeah, that would be the biggest driver, right? Is essentially NFPA and how are explosive refrigerants treated, especially in high concentration, right? So when we start getting away from the smaller unitary, like residential scale heat pumps, that's where propane is most frequently seen. But in large scale applications where you've got a really large concentration of that fuel slash refrigerant, um, that's where concern starts coming up. And I'd see less likelihood of large scale combustible refrigerants really taking hold there.
Yeah. Isaac, any thoughts or any further thoughts
I,
there?
I think that yeah, we've seen a lot of product in Europe and Asia embrace the propane, the R290 small systems. I'm talking single phase under 5 ton capacity. And so we're seeing its application in even refrigeration, some like an appliance, a small appliance, a small system for maybe your home. In terms of a large commercial sized heat pump chiller, we're not seeing that, and our codes are not ready for it. We do
Yeah.
not have a way to apply that today.
Excellent. Okay, so I'm going to ask another question that I think this might equally rile you all up, so this ought to be fun. So one of the biggest issues when you start looking at a potential electrification project, and we're applying heat pumps in general for HVAC, water heating, and all of the potential impacts you get is just a startling lack or very inconsistent set of building data, right? I think we all know that's really, really hard, right? So my question is just just super light softball question. What does the industry need to do to overcome this kind of consistent lack of building data, which is gonna, if it's not already, it's gonna be a major barrier to projects like these that we want to do.
I think one of the things that it's already starting to happen is this requirement to meter panels separately so we know where the energy is actually going in a building. And um, more times than not, especially on commercial buildings, when you look at the numbers, you find out that they're actually designed very conservatively,
Right.
not just because the engineers are conservative, but also because the code's very conservative. So if you actually go back and measure what's actually being used, more times than not, you'll find that there's a fair amount of spare capacity on the system to add this equipment in. So in a way, that's the good news is that in most cases, I think there's capacity to switch over to heat pumps and not run out of power.
Right. Awesome. So we do, by the way, have some information on project resources and engineering or data, I should say design resources that are coming from the pilots that we talked about and were mentioned by a number of the speakers. And Adam, you're going to present just a little bit here.
Yeah, just real
Make sure
quick.
we have time for that.
Yeah, just real quick. Let me share my screen again. Yeah, so with all of the challenges and opportunities that have been presented so far, it can be difficult to navigate a path towards considering this technology for your project. So, uh, ProspectSV and our partners have been busy at work developing what we're calling an industry guidance package. So, the goal of this resource is to provide the necessary information, tools to help, building designers, building owners, engineers, architects, contractors, what have you, assess the feasibility and potential applicability of integrating a CO2 heat pump into their respective projects. So here's just an outline of what we may provide and what we will provide in the package. So we're kind of tackling two approaches. First, the general design resources that will give end users and designers a good outlook of how feasible a CO2 heat pump is for your project. So Flow, for example, Flow has its own BIM objects page where you can download a 3D representation of their heat pump to use in your planning tools. We'll also have technical data sheets of the product with certain specifications regarding each model, a customer support framework, training resources, which will be supported by DMG North, thanks to Isaac, to prepare engineers and contractors for installing this technology. And then finally, application guidelines that may come in the form of a questionnaire to answer basically the central question of like, is a CO2 heat pump the right product for your building? And on the other side of that, we'll have performance metrics and results and model those out to apply to multiple use cases, whether it's presented as case studies, model performance for large commercial buildings, and then eventually with the Strauss project, with the industrial cold storage use cases, we'll provide system curves, a financial analysis comparing the net value costs of existing technology with CO2 heat pumps. And the goal is the same throughout it all, to make it easier for project teams to assess where a heat pump makes sense and how it would operate in their specific environment. So these tools kind of take the guessing out of early stage decision making to help stakeholders quickly determine the applicability for their own facilities, and thereby advancing the adoption of CO2 heat pumps. And real quickly, if I have time, just wanted to address one more question that I saw in the Q&A. What were the key takeaways from our FlexLab demonstration? So, in that one, we were evaluating how the CO2 heat pump uses an ultra-low GWP refrigerant that can replace gas-fired heating and water heating equipment. And one of the biggest takeaways was that the system was especially efficient when it was delivering heating and cooling at the same time, so in simultaneous mode. And again, this is all happening from one single unit, so that's pretty cool. Other takeaways was a plug and play installation of the heat pump system at FlexLab really simplified the installation process. So the heat pump was pre-assembled and then trailer mounted for ease and transportation on-site installation. And finally, another cool one, if you visit the heat pump and see it in action, you can tell how quiet it is. It's about 60 to 65 decibels is the sound level. And that's compared to a typical system, which is around 75 to 80 decibels. So that's like me talking to you, in a normal conversation compared to being right next to really busy city traffic, basically. So that's also one of the really cool takeaways from it. But yeah, just to kind of round out as well, if you want to keep up on the status of these projects and then eventually gain access to the resources I provided, or just stay up to date on what we're doing and come talk to us, feel free to scan the QR code at the bottom left. That will take you directly to our Pathways program, so you can learn more about our projects and get in contact with us.
Excellent. Well, I'd like to thank everyone that has attended, and those of you that are still here. We're just slightly over time. We just did a bang up job. Thank you so much, guys. That was just an excellent set of presentations. We have contact information for everyone here if anybody would like to follow up. And there was a number of kind of detailed questions here that kind of go a little bit beyond the CO2 heat pump scaling topic, but that's grounds for continued connection. Really would encourage you to stay in touch with us. Please reach out and do join our mailing list, and we'll keep you in touch on what's happening in this space from our perspective. So again, thanks everyone. Really appreciate it. Have a wonderful day.
Thanks all.
Thank you.
Thanks, everyone.
Thank you.
Thanks.
Oh, team, stay on. Did you stop the recording?